Hi, Sudarshan. We'll just start in a few minutes.
Hello.
Yeah, hello. Good evening, Sudarshan. We'll just start in a few minutes, okay? In maybe 2 or 3 minutes. I'll just share my screen that time. Meanwhile, can you tell me if my screen is visible?
Yes, sir. Visible, sir. Screen.
Okay, okay. Thank you. I'll just wait for 1 or 2 minutes and then we can start, okay? Okay, so then we can start. Good evening and welcome again to this problem solving session for this advanced power electronics and control course. So this will be the week 5 of the problem solving tutorial sessions. So in this week, I guess you went through the Chu converter and then you covered in detail about its steady state analysis, and then you went ahead with chopper circuits. So you had the class A, B, C, D, and D chopper circuits, or in other words, you studied about one quadrant choppers, two quadrant choppers, and finally four quadrant choppers. You studied multiple topologies and you classified them as classes A, B, C, D, and E, right? So after covering the chopper circuits, you went ahead with SMPS, that is switch mode power supplies, and you studied in detail about isolated DC-DC converters. So you were introduced to flyback converter, then the forward converter and the push-pull converter, right? And finally, towards the end of the week, you also had some discussion on half bridge and full bridge based topologies. So you will eventually see that based on this half bridge and full bridge, you can end up with a lot of topologies, but that's for further weeks, right? Anyway, so based on these DC-DC converters, we will be solving problems. So today we will be discussing in detail about problems in the conventional topologies like the buck boost and buck boost converters. We also have a few problems on isolated DC-DC converters, which we'll be seeing as well. So if time permits later on, we might as well have problems, extra problems that we can start solving on these topologies itself. But I have tried to keep the problem set diverse so that you get an idea of different problems. Okay. Okay. So I'll just go ahead. Um, at any point, of course, if you have any doubts, you can ask me and stop me as well. Okay. So first things first, DC-DC converter can be used as switching mode regulators for dash. To convert non-regulated DC output voltage to regulated DC output, to convert regulated to non-regulated, to convert high frequency AC to constant DC output, and all of the above. So I guess this is a very simple question. The answer is, of course, A, that is to convert non-regulated DC output voltage into a regulated DC output voltage. So that's the essence of whatever you have been studying so far, right? Um, okay. The buck regulator has an input voltage of Vs equal to 12 volts. The required output voltage is Va equal to 5 volts at R equal to 500 ohms. And the peak to peak output triple voltage is 20 millivolts. The switching frequency is 25 kilohertz. If the peak to peak ripple current of inductor is limited to 0.8 amperes, determine the filter inductance. Okay. So for all of these questions, before starting to solve the question, please draw the circuit diagram. So it will help you immensely. For example, they have given that this is a buck regulator, right? So you just draw the buck converter, and then they have given the input voltage and the output voltage and the R as well, and then the peak to peak output voltage ripple as well. Okay, and the switching frequency is also given, and the delta IL is also given. So since this is something that has to do with inductor current, it will be good if you can draw the inductor waveform. Okay, so in this inductor waveform, as you can understand in a buck converter, when the switch is turned on or the main switch is turned on, the inductor kind of charges up, right? So the voltage across um, the inductor is going to be Vs minus Va during the on period, right? During the on period, the voltage across the inductor is going to be Vs minus Va. That is during the DTS period, and during the 1 minus DTS period or the D dash DTS period as we call it, the inductor is going to freewheel. That is, this diode or this switch is going to turn on and the inductor kind of freewheels, right? This switch turns off during this period, right? So during that period, the voltage across the inductor is minus VA, correct? That's the minus output voltage. Therefore, this is your inductor current. Now that you know the inductor current, you can as well find out the delta IL. Of course, you know that since the inductor is in the output side, your average inductor current is going to be same as the load current. In this case, that is going to be IA, right? So with this information, you formulate a relation between your delta IL and the voltage because the voltages are given, right? And your TS is also known, that's the frequency is also known. Just you know that V equal to L di by dt. Therefore, just follow that expression and write the expression for delta IL. That's the current ripple, right? So over here, delta IL is during the DTS period, it's Vs minus Va by L into DTS, right? Yeah. So Vs minus Va by L into DTS, that's the slope into time, right? That gives you the delta IL, correct? So just rearrange the terms, you will eventually end up with what should be the value for L, that is the inductor, right? So if you just substitute the parameters given, that is VSS12 and VS5, and all of the other terms are also given, you end up with what's the required value of inductance, that is 145 microhenries, right? So I guess this is a pretty simple problem. If there is any doubt, you can ask me, but this was just a problem that asked you to calculate the value of L, right? So I guess this was easy enough, right? Just from the ripple calculation itself, we were able to obtain what should be the value of L, right? In order to limit that ripple for this much frequency. Okay, okay. So next question, almost the same question. So again, V is equal to 12 volts and V is 5 volt and R equal to 500 ohms. Peak to peak voltage ripple is 20 millivolts. The switching frequency is 25 kilohertz. If the peak to peak ripple current is limited to 0.8 amperes, determine the critical value of filter inductance and critical value of filter capacitance. So you might know that what they mean by critical value of filter inductance or critical value of filter capacitance is that the just enough value of your inductance or capacitance which will make the system just continuous, right? It is the boundary between your discontinuous conduction mode and the critical conduction mode. So as you know, as your L increases, right? As your L increases, it goes into CCM mode, right? So because your L is too large, that the ripple is not too much. The ripple is very small. So the inductor current is almost a constant, right? So it will remain around that operating point only. On the contrary, if your L is smaller, then what happens is what you're eventually telling us your delta IL is very large compared to the average inductor current compared to IL, right? So if your delta IL itself is very small, then the delta, if your IL or the average inductor current itself is very small, then your delta IL becomes comparable to that, right? So during that condition, the converter may go into DCM mode. So there is obviously a boundary between CCM and DCM, right? Um, Based on that, they have asked you what is that value of filter inductance and correspondingly tell the value of filter capacitance, right? So this is again a straightforward question. So in CCM, you know that, okay, delta L, this is the relationship between delta L and L and for delta VC and C, right? So you may be using this formula for calculation of your inductance during normal conduction, right? During CCM. And because they have given all the values, you might just substitute that and you get what is L and C, right? So this was your previous question. Calculate the value of L for the given parameters, right? You ended up with 145.83, correct? So similarly, you can calculate for C as well for the given value of delta ripple, delta VC ripple. They had mentioned it as 20 millivolts. So this is the value of C that you need to put in your system. Okay. However, the question is not the value of L or C. The question is critical value of L or C, right? So as you know, in case you don't remember the formulas or something, it's better to draw the waveforms. Okay, so it will help you. So that's what we have done over here as well. So you know that IA is the average value of the load current, or in this case, since it's a buck converter, it is the average value of the inductor current as well. And you have the delta IL ripple. So from this itself, you can formulate that your delta IL ripple, peak to peak ripple, is going to be twice your average value of inductor current, right? So that's what we have written. Delta IL is going to be twice your average value of inductor current, right? This is going to be twice this value. Okay. So average value of the inductor current is going to be the same as your load current, which is V naught by R or VA by R. So for a buck converter, you know that it is VA is D times VS. Therefore, we have written it as something like this. Delta IL is equal to 2D VS by R. Okay. So always you try to formulate a relationship between the known quantities and the unknown quantities. Okay. Okay. So from the previous slide, I guess you know this is the formulation for the inductance, right? L is Vs into D into 1 minus D divided by delta L into Fs, right? So over here, just substitute the value of delta L because we are aware of what is delta L, right? So delta L during the critical conduction case, you will end up with this relationship. Okay. So just substitute the known parameters over here. You will end up with what is the value of LC, okay, or the critical inductance. In case you are not aware of this formula, no need to worry. Just plot the inductance curve. You know that during the turn on period or the on period, it is the voltage across the inductance. I think we drew this earlier, right? The voltage across the inductance is Vs minus Va by L, right? So with this relationship, you can get what is this relation. Okay, delta L is Vs minus Va by L into dTs. So in this also you can substitute Va is D times Vs and delta L, as we just saw now, delta L is going to be 2 times Ia. So you can just substitute in the previous relationship as well. You need not remember the value for L every time you do it. Okay, so you just substitute and you will end up with what is LC. Okay, so similarly, this is for LC. So correspondingly, you obviously have a value for CC as well, right? Critical conduction as well. So for critical conduction or at the boundary condition, you know that delta VC is going to be 2 times VA, analogous to this, right? Delta L was 2 times IA. Similarly, your delta VC is going to be 2 times VA. Okay. Delta which is going to be 2 times VA, which is 2 times D into VS, right? And then you just carry out the conventional method wherein you substitute the known parameters and then substitute for the value of delta VC. Okay. So then you will end up with what is the value of CC, and over here it turns out to be 0.4 microfarads. Okay, so this is just a computation of LC and CC, nothing else. So just you need to know how you derive your value of L, and then you of course know that delta L is 2 times IA. So just substitute it over here. Similarly for CC as well, it's the same. Delta VC is 2 times VA and just substitute it over there. You need not remember this formula every time. Okay, you need not mug up this formula. Instead, you just know how the formulas are coming, derived, and then it's a cakewalk, right? Just it will take 1 or 2 extra minutes. Okay, so till this point, any doubts, Sudarshan, or is it fine? Or am I going too fast because all of them is on the slide?
No, sir. Like it's fine, sir.
It's fine. Okay, fine. Okay, so this was a problem with the same buck regulator in a critical or CCM or DCM mode, right? Just continues. Okay, so a boost regulator has an input voltage of Vs equal to 5 volts. The average output voltage VA is 15 volts and the average load current IA is 0.5 amperes. Okay, switching frequency is again 25 kilohertz. L is 150 micro and C is 220 microfarad. Determine the ripple voltage of the filter capacitor, delta VC. Okay, this is again a straightforward problem. The question is a boost converter. So if you see that it's a boost converter, just draw the circuit. It will be easy for you. Okay, it has an input voltage 5 and output voltage of 15 volts. Load current is also given. Okay, switching frequency is 25 kilohertz. Since they have given nothing about it, you can assume that this is in CCM mode, right? Continuous conduction mode. They have given you everything, L and C as well. Determine what is the delta VC. Okay, so just draw the circuit over here. And you of course know that the average value of your inductor current is going to be your input current, right? So you have a relationship between the input current and the output current that gives you how much, that gives you the relationship between your inductor current and your output current, right? Or your D in this case. And also, as far as IC is concerned, that is your capacitor current is concerned, when the capacitor or when the switch is turned off, that is, this is your active switch, right? This was your active switch. When this switch is turned on, right? When this switch is turned on, the inductor charges up, correct? So during this period, the capacitor feeds the load. Okay, that is why your IC, right? Your IC conventional direction is taken something like this. So your IC is written as minus IA. Okay, it's in the negative direction, negative IA. Okay. So this is during the DTS period, and during the 1 minus DTS period, what happens is this switch is turned off. Therefore, the inductor freewheels through the diode, right? So this can be a diode. So the inductor freewheels through something like this. Okay. So that is why during this period, the IC is going to be IL minus IA, right? Just the KV, just KCL. IL minus IA is going to be your IC. Okay. So this is your waveform for IC. They have asked for what is delta VC, right? So if you want to know what is delta VC, you obviously need to know what is your IC, right? So if you know IC, you might go ahead and do your charge balance, right? If you do your charge balance, you're going to end up with this. Okay, delta VC is equal to IA into DTS by C. Okay, it is just I is equal to C dV dt. Right? I is equal to C dV dt. It is just this expression. This is your IC and this is your C. And dV is going to be your delta V, right? dV is same as delta V. Okay. And dt is whatever period you are going to consider. Okay. Your IC is equal to minus IA or IC is equal to IA during this DTS period. Okay. This is what we are considering. Okay. So if we just substitute it over here, right? So IC is IA is equal to C into dV by dt, right? So it's delta Vc divided by dt is dTs. Okay, just rearrange this, you will get this. Delta Vc is going to be I into dTs by C. Okay, from the known expressions, you can find out what is D, right? So for a boost converter, you know what is D. What is the relation? V naught by Vn is going to be 1 by 1 minus D, right? So just rearrange it, you will get what is D. Okay, so you know what is D, therefore you can find out what is delta VC. And that's what the question is, find out delta VC. Okay, simple, right? From the known parameters itself, you can just find it out. Just the point is they have asked what is delta VC. So since they have asked something about the capacitor, draw the waveform, draw the relevant waveform. If it's about the inductor current, you draw the inductor current. Here it's about the capacitor voltage, draw the capacitor current. Okay, it will be easy for you to formulate all this, all the expressions. Okay. Okay, so this turns out to be 60.6 millivolts. Okay, so Sudarshan, so should I give you some time so that you are able to compute in your calculator? Because actually, I feel it will be good if you compute with your calculator, or can I just go ahead with this?
Yes, sir. I will calculate, sir.
Okay, fine then. Um, Okay, so then I will go to the next question. Okay, so we saw buck boost and now buck boost. The buck boost regulator has an input voltage of Vs equal to 12 volts. The duty cycle K equal to 0.25 and the switching frequency is 25 kilohertz. Okay, inductance L is equal to 150 microhenries and filter capacitance is 220 microfarad. Okay, the average load current IA is 1.25 amperes. Determine the peak to peak ripple current of the inductor delta I. Again, it's a similar question, right? You have the buck boost regulator. So first draw the buck boost converter. Okay, this should be the first step. Draw the buck boost converter. Then it has an input voltage of 12 volts. Okay, duty cycle is 0.25. Okay, since they have not given anything about CCM or DCM, assume that it's in CCM mode. Since your D is given and your VIN or the input voltage is given, you know what is your output voltage, V naught or VA. Okay, your FS is also given, L is given, filter C is also given, and the average load current is also given. Since your average load current is given, you know what is your IL or the average inductor current, right? Determine the peak-to-peak ripple current of the inductor. Simple, right? So again, draw this converter and draw the inductor current. Okay. So drawing the inductor current should be easier now, right? Because um, when the switch is turned on, the inductor charges up, right? So that's why you see the slope of Vs by L. And when the switch is turned off, your inductor discharges or it freewheels, right? Something like this. So during this period, the inductor voltage is going to be minus Va by L. Okay. So this is the cycle Vs by L for charging up and minus Va by L for discharging. Okay. So now that you know this, so this is your inductor current, right? And this is your delta IL. It's your peak to peak ripple. Okay. You know that this is your average value of inductor current. Okay. So this is your average value of inductor current. Okay. Since you are aware of this, again, you can just go ahead and do the very same thing. Okay. V is equal to L di by dt. Okay. So V in this case, during the turn on, if we see Vs is equal to L into di is delta I divided by dt is dts. Okay. So you know what is your L, right? Or delta IL, whatever in case. So here delta IL is Vs into dts by L, right? So it's your this is your first step, right? Just substitute and find out what is your delta IL. Okay. This is again a very pretty simple question. They have given you all the parameters. You just go ahead and find out what's delta IL. Okay. Okay. Um, so far we just saw the conventional topologies. Now we will go ahead with your Chuk converter. Okay. Again, if they have asked something related to Chuk converter, draw the Chuk converter. That's the first step. Okay. The input voltage of Chuk converter is Vs equal to 12 volts. The duty cycle is 0.25 and the switching frequency is 25 kilohertz. Filter inductance is L2 is 150 microhenries. You might remember that in your Chuk converter you have two L's and two Z's, right? So your filter inductor L2 is 150 micro, filter capacitance C2 is 220 micro. Okay. So both of these are the output side of the Chuk converter. The energy transfer capacitance is C1 is 200 microfarad, L1 is 180 microhenry. Okay. The average load current is IA is 1 to 1.25 amperes. Again, find the average value of your output voltage. Okay. Simple, right? So just draw your Chuk converter. Um, if you directly know the relation, determine the average value of your output voltage, just go ahead and substitute. It's just like a boost converter, right? So VA is D by 1 minus D into VS, correct? So they have given you what is D and they have given you what is VS. Just go ahead and compute what is VA or VA is minus 4 volts. Okay. And remember that in two converter, there is an inversion in voltage that happens. Okay. Therefore, it's always minus negative. Okay. It's just determine the output voltage. Okay, just go ahead and use your V naught by V in expression. Okay, so I guess this is again simple. Um, okay, so far was it fine? So that's an or else shall we go ahead with the next one? The next one is a pretty Good question, I would tell. Okay, you need to pay attention for this. So far so good.
Yes, sir.
Okay, just give me a minute. I'll just have some water, please. Okay, so we will go ahead with the next question. So please pay attention to this question. Okay, it's a very good question, I would tell, in terms of the magnetizing inductance. So you might have studied anyway. So for steady state analysis purpose, the operational conditions and power stage parameters of the flyback converter are input voltage 24 volts, magnetizing inductance is 160 microhenries, N2 is to N1, that's the turns ratio of your transformer, your transformation ratio is 0.5, filter capacitance 400 micro, load resistance 2.5 ohms, switching time period TS is 20 microseconds, or you might know it's 50 kilohertz, and duty ratio D is equal to 0.4. Determine the average magnetizing current of the converter. Okay, where N1 is the number of turns in the primary and N2 is the number of turns in the secondary side. Okay. Okay, so again, as I told, draw the converter. Okay, so this is your flyback converter. All of you might know this, right? So you have your input voltage and then you have a transformer which separates your output. So you have a switch over here and then switch over here. But read the question properly. They have given something related to your magnetizing inductance, right? So something related to magnetizing inductance. Okay, which means that when you draw your circuit, don't draw your ideal transformer model. Rather, you draw your practical transformer model, wherein you have the magnetizing inductance as well. Okay, this is what you need to draw. If you draw this, then life is simpler. Okay, so you have your magnetizing inductance. We are referring it to the primary side. Okay, you can refer it to any side, primary or secondary, but over here we have referred to the primary side and we call it as LM. Okay, draw this circuit. So then life is simpler for you. Now just do the same analysis. So what happens when this switch is turned on, you know that this LM is going to get charged, right? So the current is going to flow something like this. Okay. This inductor charges up, this capacitor supplies your load. Okay, during this period. And that is what we have drawn. This IM charges up or it rises, the capacitor feeds the load, right? That is why it's going to be minus IA. This is during the DTS period. Okay. So what will be the slope of this IM? The slope of this IM is going to be the voltage that appears over here, right? That's going to be your VS. Okay. And during when the switch is turned off, right? So the switch is turned off. So therefore the inductor or the magnetizing inductor freewheels through this, correct? It will freewheel through this. Okay. So this switch gets forward bias or the diode gets forward bias, and this is how the inductor freewheels. Okay. Therefore the inductor current drops over here and the capacitor current is by KCL, right? So you have an IM current coming over here. It's referred to the secondary side. Therefore, it's going to be IM by N, right? So IM by N, where N is your turns ratio. So IM by N minus IA, right? So this is your IA. Therefore, your capacitor current is going to be IM by N minus IA. You draw this, then life is simpler for you, correct? So just apply capacitor charge balance because it has something to do with your magnetizing inductor current, right? So you have your IM by N term over here, just apply capacitor charge balance. Therefore, um, during the D period, the capacitor current is IA, and during the 1 minus D period, it's going to be IM by N minus IA, right? Therefore, you will end up with IM is equal to N times IA by 1 minus D. Okay. So what was the question? Um, The question was compute your average magnetizing current, right? So just apply capacitor charge balance and you will end up with what is IM. IM is equal to N times IA by 1 minus D. I guess everything is given, right? So you just need to find out what is IA. What is IA? IA is VA by R, right? IA is VA by R. Okay. So VA, is N into D by 1 minus D into VS in a flyback converter, very similar to your buck boost converter, right? So VA is N into D by 1 minus D into VS. So your N was given as 0.5, that is N2 is to N1, and then your D is also given. Okay, VS is also given. Find out what is your output voltage VA. Once you know what is your VA, you find out what is IA, right? So you find out what is IA, that is IA is equal to V by R. Therefore, your IM is also known. IM is N into IA by 1 minus D. That's what we derived now. So it turns out to be 2.667 amperes. Okay, simple. Um, so you have any doubts over here, or is this fine? I will anyway explain this once again, or can we? Yeah, yeah.
So can you explain the IM concept?
Can I explain what?
IM concept, sir. IM, sir. IM.
Okay, okay, okay. This expression, right? Okay. So as I told, the first thing that you need to do is draw the converter. Okay. And over here, they have got something to do with your magnetizing inductance, right? So just draw the circuit with the magnetizing inductance. Okay. Sorry. Yeah. Just draw the circuit with magnetizing inductance. So once you have drawn it, you know that there are two switches in a flyback converter, right? This is your main switch. Sorry. Yeah, so this is your main switch, and this is of course your freewheeling diode or something. Okay, it is to be a diode. Okay, draw with the circuit. Okay, with the switches. Now just analyze when the switch is on, what happens. When the switch is off, what happens. Simple. Okay, that's the thing that you need to do. When the switch is on, what's going to be the result? Just a second. Okay. So what you need to do is just draw the equivalent circuit and analyze what happens when the switch is on and when the switch is off. So during the DTS period, right? So as you can see in the zoomed in region over here, during the DTS period, what happens? The switch has turned on, right? So that's why I have drawn the um, equivalent circuit, something like this, right? So what happens? The inductor kind of charges up, correct? So the inductor charges up. Um, okay. So the inductor charges up. Right? This is the equivalent circuit. So the inductor current rises. So what happens to the capacitor current during this interval? This diode is reverse biased, right? This diode is reverse biased. Therefore, the capacitor discharges to the load. Okay, the capacitor only supplies your load current. Similar to your boost converter. What happens in a boost converter during your on period, correct? Or in a buck boost converter as well. Okay. Therefore, your capacitor current is going to be minus IA. Okay. So this is during the DTS period. Now what happens during the 1 minus DTS period? This switch turns off. Therefore, this is reverse bias. This connection is gone. The inductor current forces this diode to get forward biased. Okay. So now you know that this current or the inductor current is termed as IM. Okay, this current is IM. And the transformation ratio is 1 is to N. Okay, N2 is to N1 or N1 is to N2 or 1 is to N, however you may want to call it. Okay, so the transformation ratio is 1 is to N. So you have an IM in the primary. If you take it to secondary, what happens? It becomes IM over N, right? Where N is your turns ratio. So IM over N, that's the transformed current of your magnetizing inductor current. Correct. Magnetizing inductor current in the primary is Im. In the secondary, it becomes Im by N. Correct. So far so good, right? So at this point, I have got Im over N. Okay. Sudarshan, can you just tell me if you are with me so far?
Yes, sir. Yes, sir. No worries.
Okay. Now at this capacitor terminal, you apply KCL. What happens then? Im by n, sorry, Im by n minus Ia, right? Im by n minus Ia will be your IC, correct? Your IC is going to be Im by n minus Ia. Okay. That is why during the off period, it's going to be Im by n minus Ia. So you're of course aware of something known as capacitor charge balance, right? So
Sir.
under steady state, they have given in the question itself that steady state analysis. Under steady state, there is capacitor charge balance, correct? That is how much the capacitor charges during the on period is equal to how much the capacitor discharges during the off period, right? Or the charge gained by the capacitor is going to be zero, right? During the entire interval, net charge is going to be zero, correct? It will not gain any charge, it will not gain any, lose any charge. That's the idea. So you apply that particular principle, which means that the area over here is going to be the same, correct? So in this IC curve, your area, this is the negative area, right? And this is your positive area. Okay. The areas are going to be same. Got it? That is the idea. Okay. So either you apply that or you just directly multiply the current. It depends on your wish. Okay. So the area is same. Therefore, what happens? It is IA for this DTS period, correct? So D into IA. I have neglected TS because anyway you are going to get TS term here also and here also. Okay. So D into IA during this period. I'm sorry. Yeah. So D into IA, that is the negative area, is equal to 1 minus, okay, I'll just write D into minus IA is equal to, what happens over here? The area is 1 minus D into this particular current, right? Im by n minus Ia. Okay. You are just supposed to solve this particular thing. You will get what is Im. Got it? So it's your negative area and then you have your positive area. Just equate both of these. So D into IA, right? D into IA and then 1 minus D into this particular current, average current, Im by n minus Ia. Okay. Just equate it and then solve for Im. Solve for Im. I mean, when you equate it, you can write it something like this expression, right? D into minus Ia becomes D into Ia if you take it on the same side, right? So Im becomes n into Ia by D. Got it?
Sir, can I
Huh.
ask
Tell.
one sir question? Sir, can I ask you one more doubt, sir? Like,
Yeah, sure, sure. So wait. You can ask me one more doubt. So, in this particular thing, is there any more doubt, or is that doubt related to something else?
sir, yeah, sir, related to this, sir. Like,
Oh, okay, sure.
so like, if I don't have this magnetizing inductance, then sir, what would be my like secondary current in that case, sir?
Sure. Yeah. Good question. So, um, this is where a lot of people have been debating, right? So, whether you call this as a flyback transformer or a flyback inductor, right? So you got it, what I'm telling. So the idea is in an if you have an ideal transformer, let's say, right? So let me draw. So if you have an okay, I will not draw anyway. Let's say this is an ideal transformer, right? For an ideal transformer, what happens? Your LM or your XM is going to be infinity, correct? LM is going to be infinity. Okay. If LM is infinity, XM is infinity, therefore your IM is going to be 0. Correct? Got it?
Sir,
So this is something that can never happen, right? Or else your converter never works. The converter can work only because of charge balance, and charge balance can happen only because your current is something like this. Your current needs to go positive, right? Like it needs to be minus IA and then it needs to go to Im by n minus IA, and your Im by n minus IA is supposed to be a positive number. Correct? Got it?
Yes, sir.
When can Im by n by minus IA be positive? Only when Im by n should be more than IA. Correct? Only then it can be positive.
Yes,
Okay.
sir. Yes, sir.
And for this, your Im needs to be more than 0. Correct?
Yes, sir.
If you have an ideal transformer, if you have an ideal transformer, you can never get Im, you can never get Im more than 0. You will always get Im equal to 0. Got it?
Yes, sir.
People use this flyback. This is one of the applications wherein your non-ideality in a transformer is going to help you. Okay. So what people do is whenever we design transformers, right? Not for this particular application, just for voltage step down or step up, we want to keep this as large as possible. We want to have a very high magnetizing inductance, right? That is what we want.
Yes, sir.
However, when people design a flyback converter, okay, what they do is they design a transformer such that they get a particular value of inductor over here. Okay, they will design for that inductance. For example, the inductance over here, how much was it given in the question? They gave it as 160 microhenry, right? So depending on the ripple, we just saw how the current is, right? This is your ripple. Similar to how you design buck boost or buck boost converters, you will know what is the value of ripple. Okay. So depending on that, they will design that, okay, this is the value of ripple I want. Therefore, I will add a shunt inductor or the transformer inductance itself should be such that your LM is going to be 160 microhenries. Okay.
Yes, sir.
One thing is when you just design the transformer, inherently it will have some LM. Correct? When you just design the transformer, it will have inherently an LM. Okay. So it may not be, it will be very high, right? Like it is expected to be of the order of millihenries, not 160 microhenries and all. It will be some millihenries. In order to make it 160 microhenries, people will externally add an inductor in parallel so that your equivalent becomes this. Got it?
Yes, sir.
Here, LM is very, very critical for us. Okay, without LM, this is not going to work. Flyback converter is not going to work. So you understand that this is actually an application of a transformer non-ideality. Okay, and we are utilizing it. But one more thing is in a transformer, of course, you can wind it, but over here, the specialty is that observe the dot polarities, right? The dot polarities are opposite. Only then it can freewheel, correct? Only then I'm sorry. Only then it can freewheel, right? It needs to be dot over here and it should be the opposite polarity over here. Okay, that is one more thing, right? Generally, conventionally in a transformer, you have both of the dots aiding. That is what we tell, right? But over here, it's opposing. The dots are opposing. Correct? That is one more thing. And this dot is also responsible to ensure that your current freewheels, okay, or the current goes something like this during the freewheeling period. Okay. So your question as to if there is no inductance, it becomes an ideal transformer. It's not possible. Then your flyback converter will not work. Because the reason is that your Im needs to be a value which is positive. Okay, only if Im by n is positive, not only positive, Im by n needs to be more than Ia. Correct? Only then your charge balance is satisfied or else no. Okay, got it?
Yes, sir.
Does this answer your question or is it not still clear
Yes, sir.
based on the charge balance?
Yes, sir. Clear, sir. Now clear, sir.
Okay, okay, thank you. Okay, then we will move ahead with the next. Okay, so what was the point? The point is Im, you derive it as n into Ia by 1 minus d, right? This is your average value of your magnetizing current. Okay, okay. So this is your average value of your magnetizing current. And of course, see, this Im is a DC quantity, correct? Im is a DC quantity, right? It is having a ripple and it has a DC average value. If you have your IM equal to 0, right? That means that it's like something, of course, your transformer as a unit cannot take DC current, right? So you need this inductor over here so that it is able to take this DC current. Transformer, of course, cannot take DC current, right? That is one more thing. Okay. Sorry. Okay. So you got your value of IM. Once you get what is IM, you just substitute the value of D, N, and IA. N and D are given in the problem. IA is not given. What is IA? IA is VA by R, and VA for a flyback converter is D by 1 minus D times V in, right? So that's what we have done. So I'm sorry, into N, that's your transformation ratio. So N into D by 1 minus D into Vs, correct? So that is your VA. Calculate what is VA, and then IA is going to be VA by R. Okay, so that is your IA. Therefore, IM is going to be N into IA by 1 minus D. Okay, so is this fine? Just we have used the transformation ratio of your flyback converter and then substituted in IM. Okay, so we just saw a very intensive problem. We'll just have a 2-3 theoretical problems so that we get refreshed. Okay, a chopper may be thought of as a dash inverter with DC input, DC equivalent of an AC transformer, diode rectifier, DC equivalent of an induction generator. So what do you think is the answer? Anyone, can you answer? Question? Any attempts? What is a chopper? Is it an inverter? Is it DC equivalent of an AC transformer? Is it a diode rectifier or what? DC equivalent of induction generator. Yeah,
B, sir, B. DC equivalent of an AC transformer.
correct. Okay. Why? The answer is your AC transformer, what it essentially does is something like it will step up or step down, right? So it will step up or step down based on the turns ratio, or 1 is to K or K is to 1 or whatever may be your convention. It basically steps down or steps up your voltage, right? So what a chopper is doing, buck boost or buck boost. So it will give you D times Vs or 1 by 1 minus D times Vs. So that's a boost or a buck or step up or step down or both step up or step down, right? So you're operating largely within these three duty ratios, right? So D times Vs, 1 minus D times Vs, 1 by 1 minus D or D by 1 minus D or whatever. So basically what you're doing is you're modulating your input voltage. So you have your V in, you're trying to convert it into V out using these three duty ratios, basically, right? Basically, in between, you have some arrangement. So you have something like you have something over here, and then you have a load. Okay. So you have your V in and you have your V out. You're changing V in into a different voltage level, right? And then you're getting V out. Either it may be above V in or below V in or both, right? Basically, you're changing it. That means that you are having a step up or a step down. That's why we tell the equivalent to be something like this. The equivalent representation is something like this. Okay. 1 is to D. 1 is to not D, 1 is to F of D. Okay. Where this F of D is your transformation ratio D or 1 by 1 minus D or whatever. Got it? Is this clear? So you have a equivalent transformer model and the turns ratio is actually 1 is to F of D. F of D is V naught by V in. It is V naught by V in. It can be D, it can be 1 by 1 minus D, it can be D by 1 D by 1 minus D, minus D by 1 minus D, N into D by 1 minus D, whatever may be it. Okay, but it's just a transformer. Okay. Let's say we call it DC equivalent of an AC transformer. We call the choppers also as DC transformers. Okay. If someone tells you it's a DC transformer, yes, chopper can be thought of as a DC transformer. Okay. So average value of output voltage of non-isolated DC-DC converter is controlled by current limit control. Yeah, Anbhuvan, I think you wanted to tell something. Hello? Yeah. Sorry, step up and step down can be called as voltage, sir, in DC-DC converter. Yeah, of course. Correct. You're right. So step up and step. Basically, you are stepping up and stepping down the voltage only, right? V into V naught. You're converting with the DC-DC converter. Yeah, of course, you're right. That's why we are calling it as DC equivalent of AC transformer. Okay. The average value of output voltage of non-isolated DC-DC converter is controlled by current limit control. This control is possible in which type of load? I think we saw this in a previous class as well. The answer, if you remember, is going to be inductive. Um, okay. However, so what do you do in any non-isolated DC-DC converter? Simple, right? So for example, if you have a voltage source, right, and an inductor, okay, the voltage source alternates between +5 and -5. Let's say +5, -5. Then the inductor current is going to rise and then fall, rise and then fall, right? Whenever it is +5, the dI by dt is going to be positive, and whenever it is -5, the dI by dt is going to be negative. This is during an inductor. When you have a resistor, you can understand it's going to be something like this, right? This is your R and this is your L, right? It is pi by R minus pi by R, pi by R minus pi by R, something like this, correct? So they are telling, right? So they are telling that the average value is controlled by current limit control. Okay, current limit control means you have an I max and then I min. So where is this possible? Obviously in an inductive load, right? Because you have something like, okay, so this will be your I max. This is your I min. So what they might do is something like when it hits the limit, right? When it hits I max, they will turn off the active device. So the inductor does not charge anymore. So the inductor will start discharging or it will start freewheeling. Okay. So this is called current limit control. If we go back to the circuit, any circuit, right? Um, okay. So if we go back to this circuit, for example, right? What they will do is you have your inductor current which is rising. Once it hits I max, right? They will turn off the switch. Okay, so the inductor will discharge. When it discharges, the inductor current falls down, falls down. When they see that, okay, it has hit I min, right? It has hit this point, they will again turn on the switch. Okay, they will again turn on the switch. So again, the inductor current starts charging. When it hits I max, they will turn off the switch again. Turn off the switch again. Therefore, the inductor current falls, and when it hits I min, they will turn on the switch again. Okay, so the cycle continues. It's like a comparator. So what they will have is something like, if you see the actual circuit, right? So what they will have is they will sense what is the inductor current. Okay, they will sense the inductor current and then have a comparator. Okay, so they will have a comparator over here. plus minus. So you'll have references Imin and Imax. They will have two comparators, of course. Okay, Imin and Imax. So it will give you the value. If it crosses Imax or Imin, it will give you a 1 or 0. Based on that, you can switch this device. Okay, based on this logic. It's a simple comparator logic. Okay. Anyway, so this is for an inductive load. That was the question, right? Okay, so it's an inductive load. In the current limit control method, same. The chopper is switched off when what? When the load current reaches lower limit, upper limit, load current falls to 0. None of them mentioned. Just now we saw, right? So the inductor current, when it reaches the maximum limit, the device is turned off. When it reaches the minimum limit, device is turned on. So the inductor starts charging once again. When the switch reaches, then the current reaches maximum limit, the device is turned off. Therefore, the load current reaches upper limit. Okay. Okay. Chopper is turned off when load current reaches the upper limit. Psi max. This is I min. In case of TRC, time ratio control, dash is varied. Duty cycle, firing angle, supply frequency, supply voltage magnitude. Okay, so this is time ratio control is another name for pulse width modulation. So you vary your duty cycle, right? So T on is varied. Okay, time ratio duty cycle or T on by T on plus T off. This is what is varied, right? Basically. T on plus T off is going to be fixed, but your T on, T on, T on, and T off are varied individually. So basically, your duty cycle is varied. Okay. So at this point, I would like to pause. So if you have any doubts, please go ahead. I'll just wait for you. If you have any doubts, please do go ahead. Okay. Okay, so we'll come back to the problem part again. We have a few interesting problems as well. Okay, so a step-down chopper has Vs equal to 230 volts, R equal to 10 ohms. For a duty cycle of 0.4, power taken by the chopper is 2097 watts. Find the chopper efficiency. Take the voltage drop across the chopper switches 2 volts. As I told earlier, if there is any question regarding this buck boost or buck boost, better you draw it. Okay. So you have your switch over here, and then you have an inductor, and then you have the diode. Okay, and then you have a load. What have they given? They have given that the voltage drop across the chopper switch is 2 volts. Okay, Vs is 230 volts. Correct? R is equal to 10 ohms. For a duty cycle of 0.4, the power taken by the chopper is 2097 watts. Find the chopper efficiency. So what is the power taken by the chopper means? It's the input power, which is 2097 watts. Okay, find the chopper efficiency. This is a simple question. What you need to do? efficiency means it is P naught by P in, right? Okay. V naught I naught by V in I in. Simple, right? Just do this and you will get the answer. Okay. Vs is the supply voltage. Um, okay. So this is the methodology. Fine. But how do you do it? That's the problem, right? So the output, sorry, P naught is V naught I naught. They have not given anything regarding V naught I naught, correct? So what you can write, P naught is actually V naught square over R, right? Because they have given you what is R, they have also given you what is your input voltage, right? Therefore, you can always find out your output voltage, correct? And it's a step down converter as well. As I have told earlier, if there is something related to V naught square over R, if there is something related to resistance, it is always your RMS quantity, V naught RMS. Okay. So what you need to do is not D times Vs, right? It's your average voltage. Your RMS voltage is going to be root over D times Vs. Okay. This is the trick over here. If you know this, then the problem is done. Okay. So that's what we are doing. So V naught RMS is what? Root over D times Vs. That is why it is going to be root over. So VR is going to be root over 0.4. Okay. Into. Okay. So what comes to the output side root over D times Vs, right? But over here, Vs is 230. You also have a drop of 2 volts across the chopper switch that we were drawing earlier. Okay, so it's going to be root over 0.4 into 230 minus 2. If I draw the circuit once again, right? Okay. So you have 230 and you have 2. So what comes over here at this node effectively to this inductor input is actually 230 minus 2, right? That is what comes to the inductor node essentially. Okay, therefore you need to consider that as the effective input voltage. Okay, so VR is root over D times Vs. One. Second thing is your Vs is not directly Vs. Your Vin, I can call it maybe Vin, it will be easier. Okay, so your Vin is going to be 230 minus 2 volts, which is the drop across the device, right? Okay, so VR is root over D times Vs. Therefore, you calculate what is VR. Okay, and therefore your P naught is going to be V naught square over R. Okay, that is your P naught. Okay, your P in is of course given as 2097 watts. Therefore, you can calculate your efficiency. Okay, any doubts over here? How it is coming? It's just root over D times Vs and your Vs is actually 230 minus 2 because there is a 2 volt drop for the device. Okay. If you have any doubts, you just please let me know now or else we can go ahead. Okay. The buck regulator has an input voltage of Vs equal to 12 volts. I think we solved this problem. This was the very first problem. The required average output voltage is V equal to 5 volts at R equal to 500 ohms. The peak to peak output voltage ripple is 20 millivolts. The switching frequency is 25 kilohertz. Everything is given. If the peak to peak ripple is limited to 0.8 amperes, determine the filter inductance. I guess the answer turned out to be 145, right? Okay. So I think we solved this problem, but just for the sake of people who join later, if there is any problem regarding buck regulator or something, just draw the circuit. Once again, there is no harm. It is the most simplest way. Okay. Draw the circuit, draw the inductor current, right? So, sorry. Draw the inductor current. Okay. Something like this. So during this period, what happens? The voltage is Vs minus VA over L, right? That is what we have drawn over here as well. Okay. So just if you know the voltage over here is minus VA over L. So just know the voltage, the time is dTs. Therefore, V is equal to LdI by dt. Correct? V is equal to LdI by dt. Just substitute the voltage values and delta I, and dt is your dTs. Therefore, you will get what is your L. Okay, it's 145.83 microhenries. It's a simple problem, and solution is also given over here. Okay. Okay. So this was the answer, 145. Okay. So yes, this is simple. We will go ahead with the next thing. A boost regulator has an input voltage of Vs equal to 5 volts. Average output voltage is 15 volts. Load current is 0.5 amperes. The switching frequency is 25 kilohertz. L is 150 micro. C is 220 micro. Determine the ripple current of the inductor again, right? So this is something again we did some in the previous problems itself, I guess. No, we did for a buck. Okay. Okay. So if there is something like this, just draw the boost converter. So you have something like have the inductor over here, you have the switch, and then you have a diode, right? And draw the inductor current waveform as well. Okay. So what is the voltage over here? Inductor voltage is going to be Vs, right? Over L, that's the slope. And over here, it's going to be Vs minus Va over L, right? Because when the switch is on, inductor current charges, and when the switch is off, the inductor current discharges. Okay, so this is the peak to peak inductor ripple is delta IL. Okay, therefore just apply V is equal to L di dt. Okay, so Vs during the dTs period, Vs is equal to L into di is delta I divided by dTs. Okay, just rearrange the terms and substitute, you will get the answer. Okay, Vs V is equal to L di dt. Okay, so that is what I have drawn here. Okay, I should have maybe written it over here. Vs over L, Vs minus Va over L. This is dTs, this is Ts. Therefore, V is equal to L di dt. Vs is equal to L into delta I by dTs. Substitute the terms, you will get the answer. Delta I. Okay. So that is what we have done over here as well. You will get 0.89 amperes. Okay. So it's a pretty simple problem, I guess. Okay. A type A chopper has an input DC voltage of 200 volts and a load of R equal to 10 ohms in series with L equal to 80 millihenry. If the load current varies linearly between 12 ampere to 16 ampere, find the time ratio T on by T off for this chopper. Okay, interesting problem. First things first, what is type A? Type A means this is a buck. Okay, it's a buck converter. Just draw a buck converter. Answer is done. Right? Or you need not even draw it. Okay. So the idea is, point is they have given that it's an RL load, right? So you have an L and then an R. Okay, they have given what is the value of R and L, but it has been given just to confuse you guys. Point is, if the load current varies linearly, okay, if the load current varies linearly means your L is very, very large, right? Than R. Because if you have an RL time constant, the rise is going to be something like this. Okay, but if your L is very large, then what happens? Your rise becomes almost linear, correct? Your rise becomes almost linear. Okay. L is very large. Therefore, you can neglect L for this question because load current varies linearly. Find the time ratio T on by T off for this chopper. Okay. So what is T on by T off? For a buck converter, you know, V naught is equal to D times V in, right? Therefore, V naught over V in is equal to D. D is what? T on by T on plus T off. Okay. They have asked you what is T on by T off. It's simple, right? You just rearrange the terms, you get the answer. Okay. Okay. So input is given as 200 volts. Okay. R is equal to 10 ohm. R is given. R is 10 ohms. Okay. Load current varies linearly between 12 to 16. Okay. So between 12 to 16, it is Imax is 12. I mean, Imin is 12. Imax is 16 amperes. So what is your IL average? IL average needs to be 14 amperes. Correct? Because 12 to 16 is the inductor current, therefore IL average is 14 amperes. If your IL average is 14 amperes, your I naught average, what is I naught average? Your I naught average is going to be 14 amperes, right? Because in a boost buck converter, I naught average and IL average both are same, right? So I naught is 14 amperes, therefore V naught is going to be I naught into R. Okay, so 10 into 14 is going to be 140 volts. Okay, so V naught is 140 volts. Simple, right? You got it. Just V naught by V in is D. D is T on by T on plus T off. You know V in. They have given you I min and I max. Therefore, you know what is I average. If you know what is I average, you know what is I naught. If you know what is I naught, V naught is I naught into R. Therefore, you know what is V naught. Okay. Just rearrange the terms, you will get the answer. Average load current is 14 amps. So average load voltage, you know, duty cycle is D is T on by T on plus T off. Therefore, you get what is T on by T off. Okay. Okay. Um, Before we go to this question, I think there was a problem. I'm sorry from Anbuvan. The question was, why are we getting a D over here, root over D? Yeah, over here, right, Anbuvan, in this efficiency problem. Why root over D? Okay, so from the basic definition of your RMS, what is RMS of any quantity? It is root over 1 by T total time period integral 0 to T. What is the function of f dt, right? F of t dt. Okay, that is the basic definition of your RMS, right? So from this only we are getting so root over 1 by T integral 0 to dts. Correct? Integral 0 to dts. So what is the function? The idea is that it's a step down chopper. That's a buck converter, right? So for a buck converter, your input is connected to output during the D period, right? During D period, its input is connected to output. During the 1 minus D period, it is 0. Okay. Therefore, it is V in, right? So V in dt. Okay. So 1 by root T root over sorry, f square of t dt, bn square, bn square into root over dts. Got it, Anbhuvan? Any doubt? If you have, can you unmute? Is it possible, or you can just type in the chat box? RMS value for R means root. Please explain RMS for RLC. I'm not able to understand your question actually. Please explain RMS for RLC means what? It is just V naught RMS. I am explaining how we derive V naught RMS. Okay, you type, I will try to explain. RMS value of LC. Where is LC here? You are talking about this problem only, right, Anbhuvan? V naught RMS of L. One question, you're talking about this problem only, right? Okay, so V naught RM, where else if we see what RMS? Okay, wait. Just a second. Not this problem. You don't have anything in this question 15. You can just type in the question number also if you see the question number. So this was 14. I guess we didn't see RMS anywhere else actually. Not in this question. Not in these questions actually. In this question, here also there was no mention of RMS, I guess. I'm sorry, Anbu, and I'm not able to catch your question. If you can type in the question number, it will be helpful actually for me also. Here also it is not there. Okay, so generally, what is VRMS of L? And there is nothing called VRMS of L as such, actually. I'm not able to catch your question. Okay, no worries. Anyway, I will upload these slides in the drive. So later on, if you have any doubts, you can anyway ask in the forum. We will be happy to answer you. Okay, so for now, you'll just proceed, but yeah, you can always catch up with us. Not worry. Okay. Fine. Sorry, Anbuhan, for that. Like I tried, but I'm not able to catch your question. Okay, so this will bring us to the last question planned so far. After this, if you have time and after discussions, if you have time, we can anyway see some extra problems. Okay, this is another interesting question. The relationship between the critical inductance in the load circuit of a step-down chopper and D into 1 minus D. D into 1 minus D is what? So relate, the question is basically you have LC, you have D into 1 minus D. How are they related? Are they directly proportional? Are they inversely proportional? What? Or is there no relationship at all? Okay. Okay, so this is a simple question. Just you need to derive the expression for LC, right? What happens in a, as I told, you draw the waveform. Yeah, this is what happens if you have a critical conduction, right? So this is your IL, which is the same as I naught in a buck converter or step down chopper. This is your delta IL. So you pretty well know that your delta IL is equal to 2 times I naught, right? Delta I is equal to 2 times I naught. Okay, or that is 2 times V naught by R. V naught by R, V naught is D times V in. So 2 times D V in by R. Okay, so what is delta IL? So during this period, what happens in a buck converter? So you have your switch. Okay, so when the switch is on, you know that the voltage across the inductor is going to be um, voltage across the inductor is going to be V in minus V naught over R. Okay, so volt, so that is your slope, right? So that is your slope. So over L, sorry, this is your slope, correct? So this multiplied by dTs is going to give you your delta IL. Okay, so V in minus V naught is D times V in divided by L into dTs is equal to 2 dV in by R. Okay, got it. So I'm sorry, I just had the circuit over here anyway. Yeah. So the critical inductance, if you just do that expression that we just did, if you just solve this expression, you will end up with this. Okay. Just substitute the values, you will just end up with the value of critical inductance. You will end up with L proportional to D into 1 minus D. Okay, so that was the question. Okay, got this problem. Any doubt so far in this problem? Or is this fine? It is just a derivation of critical inductance for a buck converter. And I think we saw a similar problem in the starting itself. So that's why I just went ahead a little fast. But you can always tell me if you have any doubts. Okay. Okay. So any doubts so far? I will just pause for a moment now. If you have any doubts, please do type in the chat box, or you can also tell Sudarshan, Pavan, or Anbhuvan. Okay, so I think I should repeat once more about this critical conduction mode. Just take the use of an extra slide over here. Okay. So the idea is that um, you have your buck converter. Yeah. So this is your inductor current under critical conduction. So this is your IL. Over here, your IL is same as I naught, right? I naught, that is V naught by R. Okay. And you also have your delta IL is your peak to peak ripple. Therefore, you can write delta IL is 2 times I naught. What is delta IL? This is your DTS. You of course know that this slope, right? What is the slope? It is a voltage across the inductor. When the switch is closed, voltage across the inductor is V in minus V naught, right? That's the voltage across the inductor. So the slope is V in minus V naught by L. Therefore, delta IL is going to be the slope into time, right? So V in minus V naught by L into dTs is equal to 2 times V naught over R. So Vn minus dVn by L into dTs is equal to 2 times dVn over R. Okay. So Vn into 1 minus d by L into Fs into d is equal to 2 times d into Vn over R. Okay. Yeah. So yeah, so that's how you will anyway end up rearranging the terms. You will end up with this. Okay. So I'll just we can just pause for a few minutes. After that, maybe we can see a few extra problems as well. We can just pause here for a few minutes until we resume. Okay. So the question is, I just want to solve some extra problems on the critical conduction, okay, critical inductance. So the question is, you have got a buck converter, okay. Please take out your calculator so you can solve, okay. So the switching frequency is 100 kilohertz, okay, and the duty ratio is 0.6, duty cycle is 0.6. V naught or the output voltage is 36 volts for an input voltage of 60 volts, okay. The LC value or the inductance which ensures critical conduction is 5 millihenries. Okay, find out the value of the load resistor. Okay, they have given you all the values. So the F is given, D is given, V naught, V in are given, LC is given, or the critical conduction is given. What is R? Okay, so you can either derive it like how we derived it in the previous slide. That is L is Vs minus V naught into V naught into T on by 2 I naught, or L is Vs into T divided by 2 I naught into D into 1 minus D. You can either do this, right? Um, so what L is equal to Vs into T by 2 I naught, Vs into T by 2 I naught into D into 1 minus D, right? So you know that I naught is equal to V naught over R. V naught is also given. Find out what is R, right? Find out what is R. That's the problem. So, um, can you guys do it? Vs is 60 into T or 1 by F is 100K. 100 into 10 power 3 divided by 2 into I naught is V naught by R. So 36 by R into D into 1 minus D. 0.6 into 0.4 is equal to LC. LC is 0.005. Okay. So R, what is R? Can anyone tell? Or I will also do. R is 0.005 into 2, 36. Okay, so R should be somewhere around 2.5 kilo ohms or 2500 ohms. If you have any discrepancies, you can please let me know. Okay, it's a simple question. Buck converter, just using the expression for critical inductance, I have just found out what is the load resistance. Okay. Okay, so I will move ahead with the next question. Um, okay, so another question on the buck converter, but this is another good question. Okay, so they have given you that Vs is actually 100 volts. Okay, and the duty cycle is 0.8. R is 10 ohms. Okay, find the average value of output current, find the average value of the diode current, find the average value of diode current, and find the average value of the source current. Okay, average value of the load current, average value of the diode current, average value of the source current. For these questions, please draw your converter. Okay, so okay, so how do you find it out? So the simple things. What is I naught? I naught is basically V naught over R, right? So V naught is D times Vs over R. So what is it? 0.8 into 100 by 10, right? So that is 8 amperes. Okay. What is ID? Okay. So you understand when the diode would conduct, right? The diode is going to conduct during your freewheeling period, right? So the diode will conduct for 1 minus dTs interval. Okay. So you have your inductor current. Your inductor current will be something like this, right? So what is your diode current? Okay, just take a new slide. This is a very interesting question. So you have your um, inductor current as something like this. So what will be your diode current? Your diode will conduct only during the freewheeling period, right? Therefore, your diode current will be something like this. Correct? During the freewheeling period, it will follow. Okay. That is why. And what will be your source current? Source current will be during the turn on period of the device, right? If, I'm sorry, if this is your IL, this will be ID, and this will be IS. Okay. So during the DTS period, your source is on, and during the 1 minus DTS period, your diode is on. Okay. This is the information we know. So what we can do is, simply we can write ID is equal to 1 minus D times IL, and IS is equal to D times IL. Simple, right? So what is D is 0.8. So 1 minus D times IL is I naught, that is 8 amperes. 8. Okay, that it is how much? 1.6 amperes, and the IS is going to be D times IL, or 0.8 times IL. That is 6.4 amperes. Makes sense, right? Simple, right? This question. If you have any doubts, please let me know, or else I will go on to the next question. Okay. Okay. So we will move on to the boost converter now. I have question. Okay. In a boost converter, Vs is equal to 360 volts. Okay. V naught is 400 volts. It's a boost converter. L is 10 millihenry. Filter capacitance is 1 millifarad. Okay. The output power, or I'm sorry, the input power, or PS, is given as 4 kilowatt. Input power is 4 kilowatt. LC are given. V in V naught are given. Okay. The converter is in CCM mode. Okay. Find RMS current through the switch. Current through the switch. Okay. RMS current through the switch, and find the um, average current through the switch. Okay. Find the average current through the switch and RMS current through the switch. For example, in a boost converter, you have something like this is your switch, right? This is your diode. Find the RMS current through the switch and average current through the switch. Okay, simple. Follow the same technique. Draw it and draw the waveforms and you get the answer. Okay, so what is the output voltage in a okay? So V naught was 400 and Vs was 360, right? Therefore, V naught by Vs is equal to 1 by 1 minus D. Therefore, D is how much? D turns out to be 0.1. Okay. Now the point is, in a boost converter, the inductor current is like this. When the switch is on, the switch current is something like this, right? The switch current is something like this when the switch is on, right? So simple method, I switch average is D times IL average. And I switch RMS is root over D times IL. Root over D times, yeah, root over D times IL average. Okay. So just follow the technique. You know that the power was also given in this problem. Therefore, P is equal to V into I, that is 4 kilowatt is equal to your input volt, your, uh, sorry, input voltage is 360 into IS, right? Your IS turns out to be 11.1 amperes. Okay. So since IS is equal to IL average, what you do know is I switch average, it's D times IL average. I switch RMS is root D times IL average. Okay, just substitute it. You should get okay, so I will give this as homework. This turns out to be 3.5 amperes. This you can compute, right? Like zero point 0.1 into I average. So 1.11 amperes. Okay, so we have seen around 20 problems today. This is where I would like to conclude. So this question was simple, just a boost converter. If we wanted you to find out the RMS value of the switch current and the average value of the switch current. So just relate it with the inductor current. Okay. Just relate it with the inductor current and yeah. Yeah, D is equal to 0.1 is very less. Of course, the point is that in terms of efficiency, if you see, okay, it's a good question. In terms of efficiency, as far as a buck converter is concerned, a high value of duty is good for efficiency. Okay, that means that the bucking operation is not too much. Okay, if you do from 20 volts to 18 volts, that is also a buck. 20 to 2 volts, that is also a buck, right? You will see that 20 to 18 volts has a higher efficiency compared to 20 to 2. Okay, analogously, for a boost converter, high boost operation is always not beneficial. Okay, so for example, 20 to 200, there is a boost. Okay, and 20 to 40, there is a boost. Even that is too much. Let's say, for example, 20 to 25, there is a boost, and 20 to 50, there is a boost. You will see that 20 to 25 has a higher efficiency compared to 20 to 50. If you want to get a lower boost, then it means that you obviously need to have a lower duty, right? In a boost converter. That is why they have given 0.1. 0.1, 0.2, these are duties which give you a higher efficiency. That's why we use 0.1. Okay, good question, Anbuan. But yeah, that's the reason. For efficiency purposes, we never operate it with, okay, D is equal to 0.9 or something like that. We never operate. If you operate like that, your efficiency will be very, very low. Okay, good question. because you understand that what happens is if you go for a higher and higher boost, right? If you want to get a higher and higher voltage at the output, you will have a higher and higher current at the input. Correct? You will have a higher and higher input current if you want to have a higher and higher output voltage. Okay, if you have higher and higher input current, your I square R losses in the switch are going to increase too much. Okay, because you are having a higher input current. So we want to avoid that. That is why we don't go for extreme operations, high boost, high buck. We never do that. Okay, that's the reason, Anbhuvan. Okay, so um, do we have time for one more question? We do have time. We can see one more if possible. Mm, okay, in this question itself, for the very same question, find the average current and the RMS current through the diode. Okay, so I will just add to this question and then we can end over here. Okay, so the question is find the RMS current through the diode ID through this diode and average current through the diode. Okay, simple. Again, do the very same thing. This was your this was your IS, right? Input side. So how will be the diode current? Or here itself, how will be the diode current? Diode will be zero over here. During the freewheeling, it will conduct, right? And then become zero. And then during the freewheeling alone. That is during only 1 minus D period, the diode conducts. Okay, so you will see that ID average is going to be 1 minus D times IL average. ID RMS is going to be root over 1 minus D times IL. Okay, simple, right? Just the complementary of that. It is D times IL, it is 1 minus D times. So root D time becomes 1 minus root D times. I mean, root over 1 minus D times. Okay, so ID average is going to be 1 minus D times IL. That is 0.9 into 11.1. You can just compute, I think somewhere around 10 amperes you will get. And ID RMS is equal to root over 1 minus D times IL. Okay, root over 0.9 times 11.1. Just compute what that is. You will get the answer. Okay. Okay. So I guess we are almost time. I will open the floor for any further questions or uh, we can end today's session with this. Okay. If you have any doubts, you may go ahead and ask.
No doubt, sir.
Yeah, thanks, Sudarshan. Okay, so if there are no more doubts, okay, someone's typing. I'll just wait for a few minutes. Okay, okay. Thank you, Pawan. Okay, so if there are no more doubts, we can end today's session. Of course, if you are having any further queries or something, you can also take it offline. You can just use the forum for that and we'll be happy to respond. And anyway, so I guess we can conclude for today. So yeah, Have a great week ahead, all of you. I'll just stop sharing and stop the recording now. Stop the recording.